The next unit we're going to work on is organic chemistry. So organic chemistry has a lot of theory in it. There's lots of nomenclature, naming rules, drawing rules. We look at properties, and then we look at reactions of organic molecules and what you can make with them. So first we need to go over a couple of different terms about organic chemistry. As you hear the word organic being used in different ways, but it's different when we talk about chemistry. So organic chemistry, when you hear that term, it's a branch of chemistry that deals with carbon-based compounds. So all of the compounds in organic chemistry have to have carbon in them. If you just see the word organic on its own, the word organic means it's derived from living organisms. So here, it doesn't always have to mean coming from a living organism when we talk about organic chemistry, but the word organic on its own, that's what it means. If you see the term organic compound, it means that compound has to have at least one carbon, but generally there's more carbon atoms present in there. Just to contrast, the other branch of chemistry that we've seen a lot of in high school chemistry, especially grade 11, is called inorganic chemistry, where you study gases and rocks, minerals, solids, and compounds that can come of them. You might have also heard the word organic being used a lot in the grocery store. So in terms of food products, the word organic means something very different. Um, the idea that it comes from living organisms is true, but when you hear organic with food products, they're saying that no synthetic herbicides or pesticides were used on growing or protecting that particular food item or crop. That doesn't mean you can't actually use pesticides on them. It just means no synthetically made ones, so ones that are man-made. They could actually have pesticides that were derived from natural sources. But that's a discussion for something else. So if you hear those terms, don't panic. In your notes, I posted up a sheet that shows all of the different functional groups in organic chemistry. Functional groups are parts of organic molecules that give them characteristic properties and allow them to undergo particular reactions. We're not going to cover all of these in our course, but we're going to cover many of them. And today we're just going to learn the first three that are on the sheet here in the red, the hydrocarbons, alkanes, alkenes, alkynes. But this is a good reference sheet. It's got the basic structure of the molecules, um, their groups, and a little bit about their naming underneath. So this one would be a good one to come back to after a couple of lessons and use as a review sheet if you think that you like this visual aid there. So, what are hydrocarbons? Just like the name says, they're made up of hydrogen and carbon. So hydrocarbons are molecules only containing those two atoms, carbon and hydrogen. To make things a little easier, we're going to abbreviate hydrocarbons as HC. So if you see that, it's just referring to hydrocarbon. So these are the different classes of hydrocarbons: alkanes, alkenes, alkynes, and something called aromatic. We're going to learn the basic three today in this lesson, and then in the next lesson we'll learn a little bit more about those hydrocarbons and add in the aromatic ones. So, alkanes, what are they? They're hydrocarbons with only single bonds present, and when we're referring to types of bonds, we're referring between carbon atoms. So when we see carbons, you'll only see one line or single bond between all of the carbon atoms. Alkanes can only have single bonds. Alkenes are hydrocarbons that have at least one double bond present. And again, double bond referring to between the carbons. So a double bond, remember, you would see two lines. Alkynes are hydrocarbons that have at least one triple bond present somewhere in the molecule. And again, still referring to in between carbons, triple bond 1, 2, 3, or 3 lines. Aromatics are hydrocarbons based on a ring called benzene, and that one's a six-membered ring, which we'll see more about in the next lesson. So, how do we represent all of these different organic formulas we're going to see for alkanes, alkenes, alkynes, and then with other structures later on? So, there's two that you should be familiar with, especially from grade 11, molecular formulas and empirical formulas. We're not going to do any calculations with these in this part of the course, but you should be familiar with the differences between the two. Remember, the empirical formula is a condensed formula that shows the lowest or most simplest whole number ratio between the atoms. Here you would have a ratio of 2 carbons to 4 hydrogens to 1 oxygen. To compare, a molecular formula tells you the exact number of atoms in the formula. It's condensed, so it tells you the exact number, but you have no idea how they're actually arranged in the structure. They tell you nothing about the bonds, anything like that. And if we look at this ratio, you'll see that it's bigger than the molecular one below. With this slide and the next slide, when we look at different ways to represent organic compounds, we're looking at the same compound for all of the different representations. So in the next slide, you'll see 4 carbons, 8 hydrogens, 2 oxygens arranged in a few different ways. Now here are 3. There's different versions of formulas for organic compounds. First one up here, if we take a look, is sometimes called a condensed formula. You can see a little bit more of the formula expanded. If we count though, there's 1, 2, 3, 4 carbons, 3, 5, 7, 8 hydrogens, and 1, 2, 2 oxygens. You can see that this is the molecular formula before. We still have all of those atoms here, but they've been expanded a little bit. The reason why they call it condensed here is because you don't see all of the bonds. So there's no bonds shown, but you can see carbon. This one has 3 hydrogens attached to it, and this one has 2, and this one has 2, and then this carbon has a couple of oxygens and a hydrogen attached to it. The next structure shows you a lot of detail, sometimes called displayed formula or expanded formula. This is the best one to learn with when you first start drawing organic molecules. You see all of the bonds, you can count them, and it's a lot less likely that you're going to be making mistakes when you draw these ones. So if we take a look, 1, 2, 3, 4 carbons, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and then there's your 2 oxygens. But here you can see the exact bonds that are happening. Up top here with CH3, this is still the same thing. C, 1, 2, 3, CH3. This is CH2, CH2, and then COOH. This one, though, tells you lots about the molecule, how many atoms are bonded, what types of bonds are there. The next one is your structural formula. This is similar to the displayed formula or expanded formula up above, but you don't see all of the bonds. You still see bonds between carbons and oxygens or between other atoms, but where the hydrogens are, they're condensed. They're just simplified. The last one's called a skeletal formula or a line formula or line diagram. These are ones that take a bit of practice with, so this is one that I wouldn't suggest jumping right into, but once you get the hang of them, they're very easy. Here you don't see any carbons or any hydrogens on carbons and hydrogen bonds. You'll see bonds with other atoms like oxygen or nitrogen. But here you just see lines. With these ones, the lines represent single bonds. If you see 2 lines, double bonds. If you were to see 3 lines, it would be a triple bond. When you draw these ones, though, they have to be geometrically correct. So you have to keep the geometries here. Some of this geometry ties back in with Vesper from the last unit. So once we walk through a few examples together, then we'll practice how to draw these out a few different ways, just so you can get a taste for how each of them work. So we're going to start off with how to name hydrocarbons, straight hydrocarbons. These are the most simple ones. All of the naming rules are very systematic with naming organic compounds. So once you learn the basics, we take the basics and add a little twist on it each time we learn a new compound. In general, the name for an organic compound is broken down into a couple of parts. There's a prefix. The prefix will tell you how many carbons are there. There's a position number. This is there sometimes, not always, but it depends on what's present. This will tell you in the molecules we'll see today where you might find a double bond or a triple bond in your molecule. And then there's a suffix. The suffix is the ending. That's going to tell you what type of compound you have. So first, let's look at the prefixes, the first part of the name. We're going to deal with carbons between 1 carbon and 10 carbons. 4 of these do not follow the typical patterns for prefixes, but the rest do. The first 4 are different. Meth, eth, prop, and bute. Meth stands for 1 carbon. Eth stands for 2. Prop stands for 3. Bute stands for 4 carbons. After that, the prefixes are familiar ones to you. Pent, hex, hept, non, oct, non, and dex. Sometimes the A is in there and sometimes not, depending on what you're writing for the name. So how do you remember the first 4? There are a few little acronyms or little sayings that are helpful. This one I remember from my first organic chemistry high school course. Monkeys eat peeled bananas. M for meth, E for eth, P for prop, B for bute. The next part of the name is the position number. We'll deal with a little bit more on that when we get into some examples next. Let's take a look at the suffix. So there's different suffixes that you can see. ANE ending stands for alkane. And remember, alkane, we said were single bonds. ENE are for alkenes. This is telling you there's a double bond. YNE for alkyne. This tells you triple bonds. So let's try out a few examples and put these together. So when we look at our molecules, we have to first find out how long the molecule is. These are the most simple ones, so it's a little bit more obvious. But once we start looking at molecules that are a little bit more complicated, you'll see why this is important. So when I look at the first molecule, I want to count how many there are. 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. I could count left to right, or I could count right to left. 1, 2, 3, 4, 5. 5 happens either way. So here I know I have 5. I'm going to start numbering them from left to right because it doesn't matter which end I count from here. So I've got 5 carbons. Then I want to think. The first part of my name, I need my prefix, which is how many carbons I have. 5 is pent. Then would be the position number. The position number we're only going to use right now if there's a double or a triple bond. Do we see any double or triple bonds here? No. All the bonds between the carbons are all single bonds. So, no position number needed. Since all of the bonds between the carbons are single bonds, I know I have an alkane. And the suffix for an alkane is ane. So here, I'm going to put on ane. So this molecule is called pentane. Again, you can break the name down to see that it matches. Pent is 5 carbons. ANE single bonds. So I have a 5-carbon molecule all made up of single bonds between those hydrogens. All right, let's try out another example. The next one, when we take a look, you can probably see right away how many carbons there are. 1, 2, 3, 4. 1, 2, 3, 4. But now we've got something a little different. There's a double bond in there. So here, because the double bond is present, when we number our chain, we have to be careful. When we number the chain, we want to make sure wherever the double bond starts, it starts at a carbon with the lowest number possible. So what does that mean? I could number my chain 1, 2, 3, 4, like this, left to right. And when I look here on carbon 2 to carbon 3, that's where my double bond is positioned. It's between number 2 and 3, starting at 2, going to 3. If I chose to number the other way around, 1, 2, 3, 4, I want to make sure that this numbering isn't any different, or if it is, if I'm going to use the numbering this way, where the double bond starts has to be lower than 2. But when I look, 1, 2, the double bond starts from 2 to 3. So here it doesn't matter which way we number. If you look at the molecule, you can also tell it's symmetrical. If we were to imagine chopping it in half along that double bond, you'd get 2 equal parts. So the numbering here is irrelevant. You can number it left to right or right to left. It will end up giving you the same numbering system. So let's get rid of this just so it's not confusing. And we'll go back and name now. So first part of the name always is your prefix. How long is your molecule? This is 4. So I would go to my list and look for what's the prefix with 4. When I have a look, I see that it's bute. Here, since there's a double bond present, this is where we need a position number. So this is how it works. We always look for the carbon where the double bond or triple bond starts. Here it starts on number 2. So I need to put a number 2 in the name in here. But the way that I put it in, I put a dash, then I put a 2, and then I put another dash on the other side. After I've put the position number in, then I need to put my suffix. What type of compound do I have? Since I have a double bond, this is an alkene. So an alkene ends in ene. So I put ene on there. So this is the name for that compound, bute-2-ene. And again, if we break it down, it's very systematic. 4-carbon compound with a double bond. And where is the double bond? The double bond starts at carbon number 2. So that's how it works. So why don't you pause the video and try the last example. Let's see if you can name that one. And then when you're ready to check, unpause and we'll walk through that answer. Okay, so last one we have to take a look at the molecule. Looking at it again, you can see there's only 4 carbons. But again, we need to watch the numbering. Which way am I going to number? Right to left or left to right? So if I went left to right, I would have 1, 2, 3, and 4. This way, my triple bond this time starts at carbon 1 and goes to carbon 2. If I chose to number it right to left, here you can see the numbers are different. My triple bond would start at 3 to 4. Which one gives me the lower combination? Left or right? When I look, my left to right is better because the triple bond starts at carbon 1. If I numbered it like this, it starts at carbon 3, and this is bigger. So I know I don't want to number it like that, like the one in red. So again, when I go to name this one, since it has 4, it's going to be bute again. I have triple bonds starting at 1, so I'm going to put a -1. And then since it's a triple bond, my suffix is YNE. Bute is 4 carbons, YNE is triple bond, and the triple bond's at number 1. That's what it's telling me. It starts at carbon 1. As with a lot of things with the number 1, it's often left out. So if we leave this out, you can also see this molecule often being called butane. Either one is fine, and more often you'll see if it's just number 1 in terms of positioning, they'll leave it out. So if there's no number and you see an ENE ending for double bond or YNE ending for triple bond, it's implying that it's on number 1. All right, now let's try drawing. So now that we know a little bit about the names, let's try drawing. So these ones, there's a few steps that you want to do. When you look at the name, the first thing you want to do is set up a base for your molecule. So draw the base chain with the number of carbons. Then you add in any functional groups. So right now it's only going to be double or triple bonds. And then when you're done, you're going to complete them with all of the hydrogens. So when we deal with drawing, if you remember anything about carbon, carbon is in group 4. It has 4 bonding electrons. This is its Lewis dot diagram. Anytime we draw anything with carbon, it likes to have 4 bonds around it. For organic molecules, when we draw them in structural diagrams, that's going to mean 4 lines. Carbon will have 4 lines all of the time, not any more, not any less with this. So when we draw them, that's something to keep in mind. So let's take a look at our first example, propane. Propane is the type of gas that you see in your barbecue. So what does its structure look like? So first thing I'm going to do when I look at the name, I'm going to look at the prefix. Prop means 3 carbons. So when I draw my base chain or my root chain, I'm going to draw a 3. And I'm going to draw the expanded diagram first so you can see how the bonding works. So 1, 2, 3. The carbons have to be joined by a minimum of a single bond for this to work. Then I'm going to look at the rest of my name. I see no position numbers, I just see my suffix. ANE means single bonds. So in this molecule, all of my bonds are single between the carbons, so I don't need to change anything here. Then, since nothing else is needed, I'm going to complete my diagram with hydrogens. So, how does this work? Carbon here has 1 line around it. We know carbons have to have 4. So I'm going to add on 3 more lines. 1, 2, 3, 4. And then the hydrogens go in around it. Next, this carbon, because it's in the middle, has 1, 2 hydrogens around it. 1 hydrogen and 1 hydrogen. Now it has 4 lines around it, and I filled in the hydrogens. Last carbon, it already has 1 line or 1 bond. It needs 3 more. So I'm going to put them around like this. This is the expanded diagram. If I want to change it to more of a structural diagram or one that's a little bit more condensed, this is what I'm going to do. So first carbon has 1, 2, 3 hydrogens around it. So it would be CH3. Then it would be bonded to the next carbon. It has 1, 2 hydrogens around it, CH2. Single bond between the last 2. The last carbon has 1, 2, 3. So when you're first drawing these, the best recommendation I can give you is do the structural diagrams. Yes, it's going to take a bit more time and a bit more space up, but then you'll be able to start to see the patterns. Why are there 3 hydrogens on the end with this carbon, or why there are 2? It has to do with the bonding. So start with this, and then you can practice the condensed, because this is a very common way you'll see organic molecules represented. Next up, hex 3-ine. So why don't you give the last two a shot if you think you're up for trying these out, and then we'll walk through the two examples together. So you could pause and try those, and then we'll continue going through the answers. All right, hex 3-ine. Hex means I have 6 carbons. So 1, 2, 3, 4, 5, 6. Then I'm going to check. I've got a position number 3, and I've got YNE, which means triple bond. So I need to count 1, 2, 3. Here's my third carbon, and starting at my third carbon, I need to put in my triple bond. So between 3 and 4, I need to add in my triple bond there. No other nuthers, no other information. Then I'm going to start adding in my hydrogens. So here, hydrogen, hydrogen, hydrogen. Now I've got 4. This carbon has 2 around it. Hydrogen, hydrogen. Next, when I look at these 2 carbons, they already have 4 lines around them. 1, 2, 3, 4. 1, 2, 3, 4. So these carbons don't need any hydrogens, but the last 2 do. This needs 2 more hydrogens, and this one needs 3 more on the end. So if I were to draw this one condensed, it would be CH3, CH2 for 2 hydrogens. I would put my triple bond in, then CH2 and CH3. Let's take a look at the last one, butene. Bute, 4 carbons. So I would draw 1, 2, 3, 4. No number, but I see an ENE ending. ENE tells me double bond. So when I don't see a number, that means the double bond must be from carbon 1 to carbon 2. So I have to add in an extra line in here. No other information, in go our hydrogens. So this carbon on the end already has 2 lines, double bond, so I'm going to put in 2. Next carbon has 3 lines around it. It needs 1 more. Doesn't matter for what we're doing right now if it's pointing up or down. Next one needs 2. And last one needs 3. And so if I want to change that into my more condensed diagram, this carbon on the end has 2 hydrogens. Then it has 1. Then 2. And the last one here has 3. So hopefully that gives you a bit of an idea of how to draw some simple hydrocarbons. Now we didn't look at line diagrams. So line diagrams, if you were to see them, would look a little bit different. So if we looked at one for propane, for example, propane over here has 1, 2, 3 carbons with it. The way that it works, I would do 1 line up and 1 line down. That would be the line diagram for propane. Where do you see the carbons? The end of a line is a carbon, where 2 lines meet is a carbon, and again the end of a line is a carbon. You see single bonds being shown by a single line in here. No hydrogens at all are shown. And when you're looking at it, you're probably wondering, well, why do we take on that kind of zigzag shape, which we saw in the previous diagram and what we see here? It's because it's actually taking on some of that Vesper and Vesper bonding. So if we look at the central atom around here, for example, there are 1, 2, 3, 4. 4 bonds around the carbon. If you remember from Vesper, that means 4 bonds, you've got tetrahedral arrangement. Tetrahedral arrangement means you've got a bond angle of 109.5. So that bond angle in there between the two carbons on each adjacent side is 109.5, which is what they're trying to show here with that zigzaggedy line. So that's something that's a little bit different. If we were to do the same thing for something like hex 3-ine, here with the triple bond, the bond angles are different. If we look at these two carbons here, these two that are there, they have two electron groups on either side. So from here to here, and from here to the next bond, these are both 180 degrees. So to make this a little cluttered, less cluttered, let's get rid of these diagrams down here. So if we wanted to draw hex 3-ine as a line diagram, I would first start wherever you see a double or triple bond to help get the bonding arrangement proper. So you would start by going 1, 2, 3. Here's one carbon and here's another. So I'll highlight it like we had before. So these are where these two carbons are. And then I'm going to continue out, since I know the bond angle between this carbon and this carbon is 180, and same thing, this carbon and this carbon is 180, I'm going to draw another line straight out, like this. My next two carbons are here and here, and the line diagram, they would be shown here and here. And then I continue the rest of my molecule. Between here and here, the last two carbons, we know that there's 4 bonds, or it's tetrahedral, so you're going to get the bonds coming on an angle. For what we're doing, it can be up or down, it doesn't matter. And same thing here, between this carbon and the last carbon, 4 bonds, tetrahedral, it can be up or down. I'll just put them both down. And then the last carbons are here and here. So that would be the line diagram for hex 3-ine. Just a note in your textbook, when they go over line diagrams with alkynes, the example that's shown is not correct. So make sure you come back and take a look at this. In the worked out example in the textbook, it is not correct. It's up to you whichever way you want to draw. I don't ever ask for one particular way for you to draw. So if you like expanded, great. If you like the more condensed one, which is common, great. If you get comfortable with line, that's fine. But you'll see questions where you'll have to name them in any of the 3 formats. So you still have to be familiar with it, but drawing it, I usually leave up to you. Now we're going to take a look at some more common hydrocarbons, ones that are not just straight chains of carbons together. These are called branches. So think about a tree. Trees aren't just one branch sticking straight up in the air. They have a main trunk to the tree, the big part of the tree, or the chain in our case. And then there are little branches that come off the side. The branches in our case are going to be made up of carbons and hydrogens, chains of carbons and hydrogens. So if we're using this analogy, this part here on the molecule would be our main chain. And then the branches are going to be coming off of the main chain. And they're going to be smaller length carbons. They can be 1 carbon long, 2 carbons long, or different lengths. Just like on a tree, the branches can be different lengths, so can these ones. When we put the names together, for these ones, they're going to be different. The main part of the chain is going to be exactly the same naming as we just saw. So all of the naming that we practice is important, and we're still going to see that come back. But now when we do some naming and some naming rules, we have to add in branch names. Since branches can go in different places on your molecule, you're also going to need to put a position number where they're located. So let's first look at what some branches are all about and how to name them, and then we'll put them together with some steps. So, branch names. Branches are called alkyl groups. The alk part of the name is for alkane, and the YL tells you branch. So, if you see YL somewhere with a name, think this is a branch off of my main chain or off of my tree. We use all the same prefixes as before, meth, eth, prop, bute, pent, and so on. So it still tells you the number of carbons, but we put YL to tell us it's a branch. So when we take a look at the first one carbon, we've got meth, and then YL, so this is called methyl, or a methyl group, a one carbon branch. 2 carbons, we have eth, YL for branch, so this is ethyl, 2 carbon branch. 3 carbons, we have prop. There's a couple ways you can see prop groups. If they're all in a straight line, 1, 2, 3, and we count where the branch comes off of, then it's just called propyl. If the branch is attached at the middle carbon, so you can see 1, 2, 3, it's attached at 2, whereas this one's attached at 1. This one's called an isopropyl group. Next, what if you have 4 carbon branches? Here's where it's attached to your tree. 1, 2, 3, 4. If they're all in a straight chain, nice like this, then it's just called a butyl group, butyl branch. But when you get into more carbons, you can have the branch attached and arranged a little bit differently. So here there's still 4 carbons, but it's not attached in a straight chain. This is called isobutyl. Here's 1, 2, 3, 4 in a straight chain, but it's attached at number 2. This is called sec-butyl for secondary. This one's called tert-butyl. If you have 3 in a chain, let's try numbering those better. 1, 2, 3. Here's the 4th one. 3 in a chain is for tert, or they call it a T-butyl group. That can also be possible. In terms of what you're going to see, though, we're just going to end up seeing the ones that are straight chain for the most part. There might be the odd example with one of the isomers in there, but you won't be tested on them. So ones where they're arranged a little bit differently, you can be familiar with them, but for now, we're just going to stick with the straight chains. One place where you might have heard some of these being used, if you've heard of isopropyl before, it might be with isopropyl alcohol, that's rubbing alcohol. So in that type of organic molecule, the carbons are arranged like this. It's a little bit different. So what am I going to do to name these branched hydrocarbons? They're a little bit different. So the first step that you want to do is still find your longest chain, just like we did, and the carbons have to be joined by bonds. So this is going to make up the trunk of your tree. If you like that analogy, this is a good one to take note of. So we were practicing that with the previous examples by counting 1, 2, 3, 4, or 5 from different ends. Here you're going to have to check all of the different ends to find the longest chain. This is going to make up your base chain. This is something that's really important, and the examples are going to try and trick you. They don't want you to find out the longest chain always the easiest way. Then once you figure that out, then you're going to go on and find any branches that extend from it. Once you figured out which ones your branches are, this is where the numbering comes in. You've got to number the chain to make sure that you always give lowest numbers first. So there are some rules with the numbering. If there are other functional groups, so like a double bond or triple bond in our case, and this is going to vary as we look at other groups later on, but right now double or triple bond. If you can give the double or triple bond a lower number first, you're going to do that, and then you're going to assign numbers to the branches afterwards. If there's no double or triple bond, then that's fine. You don't have to worry about that. You just go right to the branches and give them the lowest number. This is a hard part and requires a little bit more practice, but once you get some practice in, you'll see. Once you've done the first 3 steps, then you put the name together. So, what comes first is the position number, but it's position number for the branch. So where is the branch attached? The prefix will tell you the number of carbons. Sometimes in here you might have a position number for a double or triple bond. That will vary. And then you have the suffix you're ending, which tells you what type of molecule you have. There are a few other things that might come up, and we'll see these with some examples. What if you have more than one type of a branch? Let's say you have methyl and ethyl. Ethyl starts with E and methyl starts with M. So here you have to order the branches alphabetically, not by number. Another example, what if you have multiple branches or even multiple groups? You can group them together with their position numbers and use the prefixes like di, tri, tetra, and so on, if that's a possibility. And again, we'll take a look at some of those as we go on. So let's start with a basic example. Here's my molecule, 1, 2, 3, 4. 1, 2, 3, 4. I could count left to right, 1, 2, 3, 4, 1, 2, 3, 4, like we have. But now I've also got this branch. So when I'm counting, I also want to consider if I start numbering from here, I could go 1, 2, 3, or 1, 2, 3, or I could go 1, 2, 3, 4, 1, 2, 3, 4. Here I have to check all of the ends of my molecules when it comes to finding the longest chain. The longest chain that we found by counting is 4. And to keep it easy, we'll just keep it straight across. So here I'm doing step 1, identifying my longest chain. Then I have to think about the numbering and the branches. So here it's obvious there is a branch. If this is my tree trunk, this is my branch that's coming off. Then I have to number where the branch is attached. So I could count from left to right, 1, 2, 3, 4. And my branch is on carbon 2. Or if I count the other way, 1, 2, 3, 4, then my branch would be on number 3. So looking at this, I want to number left to right because here my branch is on carbon number 2. It's a lower number than carbon number 3. Now I can try and put the name together. So first thing that comes is the position number where my branch is. It's on number 2. So I'm going to write down the number 2. Then I put a dash beside it, just like we saw with other numbers. Then I need my branch name. This is my branch, made up of 1 carbon, so I know it's meth. And since it's a branch, I put the YL ending. So I've got 2-methyl. There's no other branches here, so I can move on to the main part of my chain, where I put in my prefix. 1, 2, 3, 4. My prefix is going to be bute. To do that, I put it right next to the methyl. No spaces here. It's all one word. Are there any double or triple bonds? No, there are not. So I don't need a position number here. So I can just go on and look. All of these are single bonds. So I've got butane. So when I put this all together, I've got 2-methyl butane. Now let's take a look where we're doing some drawing. So what if I wanted to draw these ones? So if I'm drawing these guys here, I have to look, there's a lot here that seems a little bit tricky, but once I break it down, it's not too bad. So when I'm drawing, the first thing I want to do, like before, is find my longest chain. It'll always be at the end here. Pentane means I have 5 carbons. So 1, 2, 3, 4, 5. Okay. Then I'm going to look. I have ANE ending. Everything's all single bonds. So I don't need to change any of the bonds that are here. But then I can see I have 2 branches. 3 ethyl and 2 methyl. Before we actually add those in, you can take a look, and this shows that alphabetical rule. There's 2 branches, but do you see the names here? One starts with E, one starts with M. Ethyl is listed first, followed by methyl. E before M. Even though the numbers aren't in order, the position numbers can always change, but the type of branch is always designated by the prefix there. So this is showing you that alphabetical rule. Then I have to put these in. When you draw, you can number it whatever way you like, but I would just suggest keeping it left to right so it makes it a lot easier. 1, 2, 3, 4, 5. Those are my 5 carbons. So I'm going to start putting in my branches. On carbon 3, I have an ethyl. So that means a 2 carbon branch. Since I ran out of room, I'm just going to put it off to the side here. Okay. Then I'm going to put in my methyl. 2 methyl. On carbon number 2, I need a 1 carbon branch. You can put it down or up. I'm going to put this one up like this. So ethyl, 2 carbons. Methyl, 1 carbon. 1 carbon branch on number 2, 2 carbon branch on number 3. If there's nothing else to put in your molecule, then you go in and put in all of your hydrogens. So it's a little bit cluttered when you have these big branched ones, but it still works. For branches, you can put them all in, or if it's easier just to condense them like that, you can definitely do that. I'm going to do that here just for some space. And then we'll put in the other hydrogens here. There we go. Now, if we wanted to draw this in the condensed way, instead of drawing out all of these bonds, 1, 2, 3, CH3. Here I've got CH, and then I'm going to put my branch on it there, CH3. Next one, CH. Then I have my ethyl branch down here. Then I've got CH2 and CH3 on the end. So if you want to try drawing one out, pause the video and see if you can draw example number 2, 2,3-dimethyl butene. Sounds intimidating again, but break it down first with your main chain and then add in your branches and other functional groups. All right, so let's try this one out. I'm going to start with bute. 1, 2, 3, 4. 4 carbons. I have something happening on carbon 2. It's a double bond. So 1, 2, 3, 4, starting at carbon 2, I've got a double bond. I put that in there. Then I've got a couple of branches. Now here you'll see something different. This is following that rule that we listed before, using prefixes di and tri for multiple branches. So you can see there's a di in here. Dimethyl, it means two methyl groups. Where are the methyl groups? One is on carbon 2 and one is on carbon 3. When there's multiple numbers of the same group, you use a comma to separate them. So, carbon number 2, I'm going to put my methyl. Carbon number 3, I'm going to put my methyl. You can point them up, down, or on one side and one on the other. At this point, it doesn't matter. Then I'm going to put in my hydrogens. So, on the end, I need 3. This one will need 3, or I could condense them all right away, which is fine. So I could do it like this, or you could write it like this. Either one is acceptable. These carbons don't get any hydrogens because they already have 4 lines. 1, 2, 3, 4. 1, 2, 3, 4. Again, this is one reason why doing the expanded diagrams first to start to see some patterns is helpful, because you don't put in too many hydrogens. On the end, I need 3 more hydrogens, so I put them in like this. Then if I wanted to draw it in the condensed version, and again, if you haven't tried this, you could pause it quickly and check. This way is the most common way you'll probably see them being represented. On the end, CH3. Then I have carbon with double bonds. Each of these have your methyls. And then on the end, CH3. And again, if it's helpful, you can always write in the numbers too. We didn't do this for both of them. 1, 2, 3, 4. Methyl on number 2. Methyl on number 3. 2,3-dimethyl is where you see the name. If you want to even add in the numbers up here, that's helpful to follow along. You do what you need to do to make sure your diagrams are clear. Last but not least, we're going to try naming. So drawing are easier than naming when dealing with the branches because they've already done all the hard work. You just have to break it down and draw it. When you're given structures, this is how they might look. They're purposely confusing and a little bit weird because they want to make sure you follow all of those rules. Find your longest chain, find the lowest numbers, put the name together. So when I look at my first example up here, I want to count from all possible ends to see what my longest chain is. So I could go 1, 2, 3. I could go 1, 2, 3. I could go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Or I could go 1, 2, 3, 4, 5 like that. Or 1, 2, 3. You can see there's lots of possibilities. When I look at my molecules, check all of the different ends that are there to make sure that you find the longest chain possible. The longest chain also has to include the double bond, and definitely that will work here. So 5 was the longest. So what I'm going to do is outline the trunk of my tree. You can do this with a highlighter at home or with a pencil, whatever is easier. Then I have to think about the numbering. Here's my double bond. I want to give it the lowest number possible. If I were to number it left to right, the double bond would start at number 3 and it would go to number 4. If I numbered it the other way, right to left, you can see that by going right to left, 1, 2, 3, 4, 5, this would be 2, and this would be 3. 2 and 3 are a smaller combination than 3 and 4. So when I number this one, I want to make sure I number right to left. So let's get rid of this, and we'll number it the correct way, right to left, for reference. I also have a couple of branches on this structure. They're both 1 carbon each. They're both methyl groups. So now I'm ready to put this together. So my branches go first. Since these are both the same type of branch, I'm going to group them together like we just saw. So when I go with the name, I'm going to put the position numbers first, separated by a comma. 2 and 4. Then I'm going to put di because I have two of them. And they're both methyls, so I can put it in right away. So far I have 2,4-dimethyl. Then comes my longest chain. 5 carbons long is pent. Then I have to put in where my double bond is. Since it's starting at number 2, there goes my position number. And double bond ending is ENE. So this one's called 2,4-dimethyl pent 2-ene. So the next two are a bit challenging, but to see where you might go wrong, I'd strongly suggest pausing and giving these two a fair shot on your own without checking any of the answers that you see from me. See if you can name them, and then we'll walk through the answers next. These two are purposely meant to be a bit confusing. You will get caught up in a couple of spots, but that's how we're going to learn some of the rules. So give it a pause, and then when you're ready to check, come back in. Okay, so let's see what's going on with example 2. We said we have to find the longest chain that includes any functional groups. So here I can see there's a double bond. I need to make sure when I number, it has that included in the chain. So let's just count what the longest chains could be and see whether they include the double bond or not. I could go 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. 1, 2, 3, 4. I could go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5. You might have heard the number 7 jump out like this as being the longest. Yes, there is a chain that is 7 long. I'm just going to number this for reference as we're following along here. But the problem with this is it doesn't include the double bond. The double bond is not going to be treated as a branch in this case. The double bond has to be part of the longest chain. That could mean, yes, you could have a longer chain, like this in this case, 7, but since it doesn't include the double bond, it won't work. The longest chain that you make has to include a double bond or a triple bond if it's present. So what we're going to do, erase these numbers because this chain does not include that double bond. And we need to look at options including the double bond. 1, 2, 3, 4. That's probably too short. 1, 2, 3, 4, 5. Okay, that's a bit longer. 1, 2, 3, 4, 5. But what if I do this? 1, 2, 3, 4, 5, 6. If I number it like this, then I get a 6-carbon chain. Yes, it's drawn weird. In real life, no one would draw this molecule like this. But in the practice examples that you will see, they're purposely trying to make sure you can practice your numbering. So, 1, 2, 3, 4, 5, 6. I could number it like that. Or I could start down here and go 1, 2, 3, 4, 5, 6. The reason why I'm going to start numbering up here is it's going to give my double bond the lowest number, starting at number 1. If there's a double bond or a triple bond at the end, automatically start it at number 1, because it'll always be the lowest number. Once I've done that, then I can look and see I've got a bunch of branches going on. I've got an ethyl, and on number 4, I have 2 methyl groups. They're 2 separate, they're not joined together, so this is methyl, and this is methyl. 2 joined in a line together, that's ethyl. So now I'm ready to start putting the name together. These are methyl groups, both of these. This is ethyl. Ethyl, alphabetically, is going to come before methyl, so I need to put this one first. Ethyl is attached at number 2. So I put 2-ethyl. Then I need to put my methyls. There are 2 of them, so I'm going to need to put dimethyl. But since they're both attached at number 4, I have to list the number twice. One number 4 is for this methyl, and one number 4 is for this methyl. So I put 4, 4, then I put dimethyl, then I need to continue on with the rest of my molecule. 6 carbons long with a double bond on the end, so hexene. So this is 2-ethyl, 4,4-dimethyl hexene. You might be asking yourself about that alphabetical rule here. This is E, and this is M, but I see the di here. D comes before E. Again, it's by type of branch. The prefixes can change depending on what's actually attached. So even though it says di, it could have been tri if there were 3 somewhere else. Alphabetical rule is always by branch type. Ignore the numbers, ignore the prefixes. E comes before M. All right, that's the hardest one out of these 3. Let's take a look at the last example. Again, if you haven't tried it, pause it and try it. Strongly recommend you do so you can start to see how this works. So we're looking here. We've got all these ends we need to check from. But remember the rule we just went over with 2. Double and triple bond has to be part of your longest chain. So when we're counting, we want to make sure this is included. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. Okay, 7's longer than 5. 1, 2, 3, 4, 5, 6, 7. I could get 7 going up or down. So then I'm going to look around here. From this carbon, I could either go up and get 7 or down. Here it doesn't matter because there's 2 carbons down below and 2 up, and they look identical. So it doesn't matter which way you decide to go, whether you go up or down, but 7's going to give you the longest chain here. So I'm going to highlight, and why don't we just go up? When I do that, I can start to see my branches. This is going to be a branch, and this is going to be a branch. When I number, I need to give the triple bond the lowest number possible. So if I started numbering up here, I would have 1, 2, 3, 4, 5, 6, 7. 5 would be where the triple bond starts. Or if I did left to right, 1, 2, 3, 4, 5, 6, 7. Left to right gives me number 2, where the double bond or triple bond starts. The other way was 5, here it's 2. Now I'm ready to put it together. This is our methyl, and this is our ethyl. Methyl and ethyl. Ethyl is going to come first. So 5 ethyl, 4 methyl, 1, 2, 3, 4, 5, 6, 7. Got my branches in. 7 is hept. I'm running out of room here. My triple bond starts at 2, so I need to put my 2 in there, and then ending in YNE. So if you can do these 3 examples, these are some of the more challenging types that you'll run into, but the more you practice, the easier it gets, I promise. So practice as much as you can, try the assigned work. There's extra worksheets as well. If you need to do those, do those. Once you get the basics in organic chemistry, it gets a lot easier with the naming and drawing. So if you put in more work at the beginning, it'll make it a lot easier at the end.